Alright, so welcome back. Today I want to talk about the atom. I want to introduce you to the atom in a chemical sense. Now the odds are you've seen this in a grade school science class or biology, and you've got this stuff kind of in the back of your head. And lecture today is to remind you that these things exist, so when we start talking about chemistry more formally, that I can use these words without having any fear of saying, okay, do you actually know what I'm talking about? So as may be review, it may not be, I want to make sure that we all are on the same page so we can all talk the same language when we start working with chemistry proper here in a couple of weeks. To start off, we need to talk about the atom. And the atom is the very smallest particle of an element that retains the property of that element. Okay, so that's key. I'm up here. The atom is the very smallest unit of an element that acts like that element. It's true that there are smaller things than atoms, things like electrons and neutrons and quarks and leptons and bosons and all these things. And we'll talk about those soon. But those little pieces are in everything, and they're not different. What's different is when I start to combine those little pieces together, I get something kind of a little bit more. Look, if I have a box full of Legos, I could build anything I want out of it. But until it's there, it's just pieces. It's the same thing with atoms. Until I combine the protons and the neutrons in a specific way, all I have are those Legos. All I have are these basic blocks. And how I arrange them together, that tells me how it works differently. And it's hard to wrap your head around the size of an atom. So, let's say I'm over here with my orange, right? And this orange, it's pretty big. If you think about holding an orange in your hand, it's sizable. It's like the size of your hand. And inside this orange, there's exactly one atom and nothing else. So everything else is missing from the orange except for that one atom. Well, the scale is the same as that size of the orange here on Earth, right? So the ratio here tells us a really good idea of how small an atom is. It's tiny. It's inconceivably small. It's the size of an orange on the scale of a planet. Okay, it is incredibly hard to explain just how small these are. They are tiny. They're so tiny that you're made up of 10 to like the 24th atoms in your body. It's incredible how many atoms there are. I think most of you think an atom has something like this, that like you've learned that there's a nucleus in the middle here and like some electrons floating around the outside of it, and they take on this cool kind of shape where the electrons apparently are just going like, whoops, going wee, around. And, that's not bad, it's just not nearly complete. This was come up with. And this model, it makes sense to people at first because it kind of looks like the solar system. Like you got a sun, your nucleus, and Mercury, and Venus, and Earth, and Mars, and whatever. And maybe Pluto's way out here doing his own thing. But it makes sense. You'd think it would work just like the solar system, that you'd have this one fixed, really heavy thing in the middle, and all the light things are running around and flinging around each other quickly. But that's not actually how an atom works. No, like atoms actually look more like this. The nucleus, which is too small to even see in this picture, not only because of pixelation, let's just draw a little dot in there and show you. The nucleus is this small little thing in the middle, and then the electrons, they're just everywhere around here, right? I mean, in some places they're more likely to be in others, but they're just kind of like this cloud. There's no like really defined orbit where the electron's just moving around like a planet in the same path every single time. No, the electron's here. And then, some time later, it's just teleported to here. It's a probability function that dictates where the electrons are. And we'll talk all about this when we talk about quantum later in the year. But what I care about is saying, okay, I've got this proton, this neutron in the nucleus, I've got these electrons on the outside of it. And for right now, that's all you need to know. And so, honestly, even though it's not correct, the idea that you've got these orbits interacting with each other around some nucleus like this is not so bad for us. I know, it's just incomplete. But, the reality is is actually tracking an electron would be like trying to start water here and say, okay, well, which path does it take through this rapid, right? And there's no way I could model that beyond just kind of trusting that water kind of acts like this basic path as it goes through these rapids. With any given atom, there's no way I could do enough math or have enough data to actually measure that. This is the same thing with the position of an electron. Now, inside an atom, there's a nucleus and the electron cloud, which you can see in my picture over here, right? The nucleus is at the middle, the cloud is around it, and I'm just going to tell you, the nucleus is tiny. It's so incredibly small. I'm going to show you a little video here in a moment about how small it is. But it contains almost all of the mass of the atom. I mean, we're talking like 95, 98, 99% of the mass of the atom. It's all right there in this tiny little thing. So if I have a tiny little thing with a lot of mass, at least for the scale of an atom, then I know it's very, very dense. And I mean, it's incredibly dense. And the video will go through that too. And you've got these electrons just kind of flash around, wee, 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 wherever they're at, right? And that means almost everything in that atom is just empty space. Well, take a look at your desk for a moment. That's basically empty space. You're basically empty space. Every atom is more space than it is stuff, right? Most of the atom is just this electron cloud. The actual stuff, the nuclei, are so incredibly small and incredibly far apart on the scale of these things. And we'll go into this more in a detail in a moment. For now, what I need you to know, though, is that the nucleus is made of my protons and my neutrons. And we'll talk about what those symbols mean here in just a moment. So we're talking about the nucleus here at the middle of the atom. And the nucleus is made up of protons and neutrons. And those are two kinds of particles. Let's start off by looking at the proton here. The proton is positive. The proton, we write it with the symbol P superscript plus, because the word proton takes a while to write out. It's subatomic. Protons are really, really important to chemistry. We'll talk about why here in a little bit. But for right now, I want you to know is they carry a charge equal and opposite to an electron. Electrons, of course, are labeled here, E minus. So if P plus was a proton, then E minus is an electron. Now the masses of a proton and electron are very, very different. But the charges are equal and opposite. So if I have one proton plus one electron's charge, I get the charge of a proton plus the charge of an electron. I get some positive number plus some negative number. I get 0 in this case. They cancel each other out. Kind of similarly, a neutron doesn't carry any charge. It's completely neutral on its own. So we write it, as an N for neutron, and then a little 0 to tell us it doesn't have any charge. Okay, and just like the proton, it sits in the nucleus. But it has just mass. It doesn't have any charge, but the mass is pretty big. The mass is about the same size as a proton. So if a proton's much heavier than an electron, and a neutron's about the same mass as a proton, that means all of my mass is sitting right in here, right? I mean, the electrons, they contribute such a very small amount by comparison. So almost everything is sitting down there in the nucleus. And so that's what I'm talking about. Like, when I talk about that nucleus, the thing right in the middle of the atom, right? Thing in here. Okay, when I talk about that nucleus, that's like 99.97% of the mass of everything in there. So when you're talking about your weight, apparently 99.97% of your weight is coming from just nuclei in your body, and the remaining part is the weight of the electrons. And I said the nucleus is small. Yeah, it's tiny. It's 10,000 times smaller than the atom. Remember how small an atom is, right? An atom's the size of an orange compared to the Earth. So we're talking about something 10,000 times smaller than that. Jeez. Now, there is the truth, which is, if the nucleus has got protons and neutrons, I have a plus and a neutral, which means here, right in the middle, I have a net plus charge. And each of my electrons floating around, E minus, E minus, E minus, they're negative. And you know that opposites attract, so these are getting pulled in towards that nucleus. That's why they want to rotate in circles. There's a force being applied to them. Well, those negative forces and the positive forces, they're what hold the atom together, at least the electron cloud part of it. Without the charges being separated like that, the atom would just collapse in on itself. And, you know, as long as I have the same number of protons and electrons, though, I end up having an atom with no net charge, right? Because if I've got like 60 electrons and 60 protons, then I have like 60 plus 60 minus, which is 0. And all the neutrons, they don't have any charge, so it doesn't matter, because my overall net charge is going to be 0. Now, we'll talk about cases that's not true in, something we call ions. We'll cover those when I come back. But for now, this is what I need you to know, that there's electrons, protons, and neutrons. The electrons are negative, the protons are positive, the neutrons are neutral. And that the core nucleus of an atom is where almost all the mass is, even though it's tiny. That's the takeaway from these slides. So we start off looking at what an atom looks like, and maybe this is the best way of seeing it. You can see that nucleus inside of that fuzzy, ambiguous electron cloud. And that's about it. Now, when I want you to think of an atom, this is the picture I want you to think about more than the one you're used to. Just electrons near a nucleus. As long as you're there, then you're where I need you to be. Anyway, I want to show you a brief video from, I think it's a TED Talk, talking about just how small an atom really is. Now, it's a little childish, but I think it gets the point across better than anything else I've seen. It really does show you just how absolutely small this thing actually is, and just how dense it is. It gives you a real idea about atoms, which I think most of you don't actually have just yet. So I want to thank you for watching that, and hopefully you got a little bit out of it. And at the second half of what I'm doing today, I want you to start to answer the question, kind of, what makes one element different from another one? And you'll hear I've got like 3 elements. I've got some bromine, some tungsten, some uranium. And these are very different things. I mean, bromine, it's a gas and a liquid at room temperature. It's very, very easy for it to evaporate at room temperature, which is bad, because bromine gas or bromine liquid is extremely poisonous and reactive. It is a halogen, and it is mean. We don't want to be anywhere in the same room as it. On the end, right now, in the moment, you're in the same room as tungsten. It's in the light bulbs a little bit. And that tungsten has a super high melting point at like 4,000 degrees. I have to like heat this up to 4,000 degrees before it melts. It's crazy. It's completely different than bromine. Or like uranium, which we know is radioactive and used to make bombs or fuel or whatever. Maybe you don't know that when you shave it with a knife or grind it with a machine, if you make the filings too small, they catch on fire spontaneously. I want to know why so much of the uranium in the world isn't the kind that we need to make a bomb or a nuclear reaction, but some of it is. What's different about it? You know, we've been talking about the subatomic particles, the protons, the neutrons, the electrons, as being like Lego blocks. Well, how do those pieces arrange differently to make my bromine versus my uranium, right? What in nature had to happen differently to get one thing versus all the other elements? How do we know I've got bromine? How do we know I've got uranium? That's the kind of question I'm really asking. And you know, it's actually pretty true. I can arrange all of these different kind of subatomic particles into lots of different things. This is a periodic table made by someone named Theodore Gray. He's a pretty famous chemist. And one of the things he does is he tries to build like a physical periodic table. A periodic table made out of all the different elements. So you can see what each one looks like. Well, why do I get gold here, but platinum here? What's the difference between these two squares? Or why do I have gold here, and how is that different than sulfur up here? Or down here towards radon? Or whatever it is you choose, right? All these are made from the same basic parts. What determines how they get made into something that acts completely differently? You know, on a side note, if anyone ever wants to have an extra 40 or 50 grand lying around, we can build one of these tables. But it turns out, like, just putting samples of gold and francium down here and samples like that make it really, really expensive. Not to mention having liquid mercury makes it kind of dangerous. So maybe not the best use, but it is really cool to look at. I'm really thankful this picture does exist. What I want to do is show you a couple elements right now in a video. I just want you to see that we have some of them here. I want you to see them a little bit quickly so you can see they are really different in some cases. And so I want to know what makes those elements you just saw different. Remember, that's the question, right? What determines if I have arsenic or bismuth or whatever it be? And the answer, it turns out, is really simple. The answer, turns out, is just the number of protons. If I can look at a single atom and somehow count the protons in it, it's very difficult to do, of course, bordering on impossible, but if I could, then I could figure out exactly what that atom is made of. It does not matter. If I count, and I count 33 protons, I know I have arsenic. There's nothing else it can be. If I count 36, I have krypton, or 18 argon, or 17 chlorine, or whatever. If I can count the number of protons, I know what I have. It's the best identifying physical property there is. And so we call it the atomic number, which you normally write as the letter capital Z. And it has a home. If you look at the periodic table, it has a square for each element, right? And there's a mass. Let's ignore that for a moment. There's a name, okay, and a symbol. And remember, you're memorizing these for a quiz tomorrow. That hydrogen is H and helium is Hg and so on and so forth. But above that letter, there is a number. In this case, 1. And that's the atomic number. That's Z. So, with this I can say that, like, one atom of hydrogen has 1 proton. If I said one atom of hydrogen has 2 protons, I don't have an atom of hydrogen at all. I have an atom of helium, right? The number of protons dictates what I have. Not the electrons, not the neutrons, nothing else. The only thing that matters for determining what a chemical is the number of protons. And of course, this plays a role in how the periodic table is organized. If you look across a row in the periodic table, you might notice the numbers get bigger as you go across by 1 each time. If I'm over here looking at these each one, I see like titanium becoming vanadium by just adding 1 proton. But if I add 1 proton to vanadium, I get chromium, and 1 to chromium manganese, then iron, and then iron to cobalt, and cobalt to nickel, and nickel to copper, and copper to zinc, and zinc to gallium, and so on and so forth. Right? Each time I add a proton, I get a different chemical. If I look at the periodic table and I see a number, I know I'm looking at the number of protons, because there's nothing that overlaps. Number of electrons, number of neutrons, those can overlap between different elements. And sometimes they do, especially when you start talking about isotopes. But right now, protons, they don't overlap. And they never will. If I say, well, I have, let's say, I'm looking here at phosphorus. Okay, you know what? I've got a phosphorus atom, but it's got 16 neutrons. Well, wait a minute. No, phosphorus has 15 protons. Right? Excuse me, I said neutrons. I meant protons. If I say I have 16 protons, I have to have sulfur. There's only one thing with 16. It's sulfur. That's why we write the number here. So let's look at a really simple couple of set of examples here. For number 1, how many protons are in an atom of radon? So I gotta look at my periodic table and find radon, and look and look and look and look because I don't have that one memorized. And wait a minute, here it is, right? All the way down here at the bottom, radon. If I look at radon, it looks like it's got a number right here, and that number is going to be the number of protons. So apparently there are 86 protons. Okay, the next question asks, an atom of an element contains 14 protons. So what element is it? Well, I should look for element number 14, which is right here. Okay, that's silicon, Si. Silicon. That's all there are to these questions. It's just using a periodic table. So they're not so bad. I also want to talk about the mass number. The mass number is like the number here at the bottom of the little square on the periodic table. We've ignored it so far, but let's not ignore it any longer. Let's actually talk about it. This is like the mass in grams. It's in grams of the element if I have a mole of it. Now, you don't know what a mole is yet, or probably don't. And it doesn't matter much. Right now, it's just a number measured in grams. And I'll tell you, the mass number is very, very rarely a whole number. Normally, it's relatively close to a whole number, but it's not really. Why? We're not going to cover today. We'll talk about that when I'm back. In very, very brief, it's because it's an average of different forms of the same chemical with the same number of protons, but maybe different number of neutrons or whatever. Okay. For right now, for me, right this moment, all you do is look at this and round it. So I've got aluminum here. 26.9. Well, that's really close. So I would say maybe aluminum, I could rewrite aluminum, which is element 13 with symbol Al, and it's pretty much 27. And that would work beautifully for us, right? We just need to round it, and that will help us do this a little bit more. So hopefully it makes sense. This is just the mass of a certain amount that we can compare between any set of elements, how much a certain amount of it weighs. And this mass number, it tells us some information. It tells us something because the number of protons plus the number of neutrons is equal to the mass number. So if I know the mass number and the element it's made of, I can tell you how many neutrons are in that atom. So let's take, for example, here, uranium. Uranium is element number 92. And it has a mass number of, let's say, 238. Good enough. Okay, so if the mass number equals the number of protons, let's write the mass number, I'm just going to write that like m sub n, equals the number of protons plus the number of neutrons. Then here I said it's 238, right? So 238 equals the number of protons. Well, this is uranium, so it has to be 92. Because anything with a different number of protons isn't uranium, plus x. So isn't x just equal to 238 minus 92? Isn't that just equal to like 146? So apparently there's like 146 of these neutrons in this atom. So you can see the neutrons and the protons may be very different sometimes, especially once you get to the bigger numbers. Like when you have an atomic number in the 90s, you're certainly going to have more neutrons than protons. When you're up at the top of the periodic table, often numbers are closer. But just really kind of straightforward algebra when you get here. And let me show you some examples of how this is going to work on your homework tonight here on the next slide. Actually, before I get there, let's talk about a quick summary. We know that the number of protons is the atomic number, and the number of electrons is equal to the number of protons, which is equal to the atomic number. And this here is kind of a lie, but it's going to be true for elements on the periodic table as they're written. It's not going to always be true. But for when we're working with the periodic table and pure elements, this is going to be true. So it's good enough for now. And the number of neutrons is going to be the mass number minus the atomic number, which is what we just showed. So these are the kind of the three facts you need to do the homework. Well, let's try the homework out here on the next slide. So your work right now is going to look something like this. You're going to get a big table. I think it's got like 20 rows. And it's got like 6 columns. The first column asks you about the chemical symbol. And the second column asks you about the chemical name. Okay, those are pretty straightforward. That's just looking at the chart. Then we ask about mass number, protons, neutrons, and electrons. Again, that might be some really basic algebra. Let's try one out here. On the first row, I ask about neon. So I need to look at the periodic table, and I find neon over here at number 10. So I know that I have the symbol Ne for neon. Okay, well I need the mass number. And I look, and the mass number is down here at the bottom of the square. Now neon, it looks like to me, is labeled neon, which is element number 10, Ne, and it's at a mass of 20.18. I got to round to the nearest whole number. So 20.18 rounds down to 20. So I know the mass number here is 20. And this is element number 10. So it has 10 protons, right? Because the 10 is up here. So again, I got the mass number from the bottom number and number of protons from the top number. Now it's an element, which means the number of protons has to be equal to the number of electrons. So I can fill that line in. Which leaves me for the number of neutrons. But remember, the mass number, across the top here, the mass number equals the protons plus the neutrons. And that should make it pretty easy. Because look, I've got 20 mass and 10 protons. So I need 20 to be equal to 10 plus x. It's pretty obvious this is just going to be 10. And so that row's done. Hopefully that makes some sense. Let's clean up our workspace here for a minute. Alright, there we go. Let's look at the second one. I only give you the symbol, in this case AU. And I look around, and I find it, and it says gold. Gold, element number 79. Symbol AU with an atomic mass of 196.9. Cool, so AU, that's gold. And it has a mass number of 196.9, or we'll round to the nearest whole number without using the, whatever it's called, the highlighter with the pen, to the nearest whole number. So 196.9, that's closest to 197. Now protons, it's just whatever the atomic number is, 79. And because it's neutral, the number of electrons is equal. Then only leaves the number of neutrons, which remember is equal to the number of protons plus neutrons equaling the mass number. So I get 197 minus 79. Okay, 7 minus 9, I can't do that. I have to borrow here. 17 minus 9, that's 8. 8 minus 7, that's 1. So I get 118. Okay. Let's clear out my canceling here so I can write. I have 118 neutrons. And that's all there are to these. It's just kind of filling in the chart. And I'll give you different amounts of information each time. You should never have one where you can't figure it out from a little bit of the clues. All this is like a little scavenger hunt on the periodic table where you need to put the information together. Then when we come back, we're going to start talking about changes in information chemically with isotopes and reactions, all these kinds of things. But first, we need to know what I'm talking about. When I say it's got an atomic number of 79, you need to say, Mr. Eric, that's just the 79 in the periodic table. And that means it's gold because it's got 79 protons. That's the enduring understanding I want you to get. That's all that this lesson's about. That's why you're doing the work you are. So to finish up, a quick set of reminders. You've got a quiz coming up tomorrow over the first 30 elements and their symbols. I remind you that there's a Quizlet to help you study or make flashcards, whatever works for you. Just study for it. It's one of those rare tests in chemistry where you can actually just memorize a thing and spit it back out and get an A. And again, I don't really like doing that with the exception of things that you're going to use so frequently that I think they're important enough to know off the top of your head and not just always look at the periodic table. This is going to save you time in the long run. I promise this is going to help you. So take the time to study that. Because if you do, you can come in, it's a 15-question quiz, 12 points, you can rock through it, it won't be that bad. And if you come in and just say, I'm going to guess and use kind of what I know, Mr. Nag, I don't need to study for this, it's going to show up really easily. I'm just going to tell you, I've taught this enough times, I've seen this enough times, that's not going to work. Just spend the time to memorize it, it's not too bad. Most of them make pretty good logical sense, but make sure you can keep them straight. The other thing is your sub's going to pass out the homework now, and that homework's the chart we just went over. You don't have to worry about getting this done for homework tonight. You have the rest of this class period now to work on it, and then tomorrow after you finish the quiz, and the quiz won't take the whole period by any means, you'll have the rest of that time to work on this chart. I'd budget that taking I bet you get 20 minutes or so of free time to work on this tomorrow too. Now your sub will collect where you are on Friday on this sheet. He or she will take it at the end of the next class, not the end of today, but the end of tomorrow. And we'll go over it next time we're in the class. Now remember, when we come back, you're in lab either Monday or Tuesday, depending which class you're in. So it won't be till Wednesday we can come back in here and talk about isotopes and talk about chemical reactions. But by then, this will be old hat. You'll be good at this. So we'll go through this, we'll review it. But for now, if you get stuck on this, first ask someone in the room who seems like they know what they're doing. And if they can't figure it out and you can't figure it out, then shoot me an email. I'll try to respond. Now again, I'm on a retreat, so it might take me a little bit more time than normal to respond, but I'm happy to try. So with that, thanks for putting up for a lecture that I know is kind of hard to follow along with the video. But I hope to see you again tomorrow, and good luck on your quiz. See ya.